All right, I think we're going to get started now. Welcome, everyone. My name is Adrian Liu, and I am a professor in the Department of Physics at McGill Space Institute. I'm your host tonight for our first Astro McGill and Physics Matters outreach lecture of the term. So tonight, we're honored to have my colleague, Professor Daryl Haggard, as our speaker. But before I introduce Daryl, I'd like to say a few words about an event that has been going on in the last 2 days. So as many of you who are regulars of this public lecture series know, all of us who do research in physics and astronomy acknowledge that we're humans first and scientists second. Science is done by humans, which means we're subject to many of the sometimes wonderful and sometimes ugly aspects of human life, with science and society really intertwined. And so in that spirit, I wanted to draw your attention to something that's been happening the last couple of days, which is the scholar strike in response to a lot of recent events, but also systemic issues in society. What I would like to encourage you to do is to, if you've got some time, take a look at this website that this event is about, scholarstrikecanada.ca. Which in the last couple of days has been populated by a lot of nice educational resources that I think that's very helpful to a lot of us for understanding a lot of the issues that impact both scientists and society as a whole. Now with that, I'd like to turn to tonight's event. So some of you are on Zoom, others on Facebook. Welcome, no matter what platform you're calling in from and where in the world you're calling in from. During the talk, if you can submit questions either via the Q&A function or the chat function if you're on Zoom, or if you're on Facebook, you can comment on the Facebook thread. And I will be monitoring all of this with a lot of our fantastic graduate student coordinators. And then I will pose these questions to Daryl at the end of the talk. So speaking of Daryl, it's my pleasure, my real pleasure, to introduce Professor Daryl Haggard, who is a professor here at McGill. Daryl is an expert at supermassive black holes and is a Canada Research Chair in multi-messenger astrophysics. She was part of the Event Horizon Telescope collaboration that won the 2020 Breakthrough Prize in Fundamental Physics for the picture of a supermassive black hole that you've probably seen in the news. And today she'll be telling us about observing black holes large and small. So over to you, Daryl, if you want to share your screen.
There we go. Great. Now I think I'm unmuted. Hi, everybody. Thank you very much for joining us tonight. It's a pleasure to be here with all of you. So as Adrian intimated, I'm going to be talking about black holes, a subject near and dear to my heart. So we're just going to dive right in. We think we'll dive right in. There we go. So I want to start off by just talking about this amazing image that Adrian was alluding to. So this is the spectacular image of photons and their final orbits around a supermassive black hole that sits at the heart of a galaxy called M87. So I'll come back and talk a little bit about M87 in a few minutes. But I want to acknowledge how spectacularly beautiful this image is and how truly impressive it is as an example of really human innovation and our curiosity and ability to go out there and search the world. Also, some of you may or may not know, so we have these sort of maybe a little bit clinical sounding names, or sometimes just esoteric and strange in astrophysics. So M87 derives from the Messier catalog of old. But this really beautiful image has also got an important indigenous name. So its name in native Hawaiian is Poehi, which is the generative darkness of creation. And so this name was derived from the creation poem Kumulipo of the Hawaiian native Hawaiian culture. And I think put this here partly because I think it's a beautiful name and a lovely acknowledgement of Hawaiians, Native Hawaiians, and other indigenous cultures' long history with astrophysics, but also to remind all of us that indigenous peoples have not always been fully involved and engaged in our astronomical pursuits, and we rely heavily on some of their sacred and religious territories in order to execute our observations. That's no less true of this beautiful image. And so this is both an acknowledgement of the indigenous lands that we are on here today, many of us, and to the great contributions that those peoples have made directly or indirectly to the science that we'll talk about. So what about this amazing Powahī, this incredible supermassive black hole? So just a little bit of sort of background information. So the supermassive black hole has 6.5 billion times the mass of our own sun. So that's pretty amazing. And that sounds like a really large number, but maybe even more amazing than the enormity of 6.5 billion times the mass of our own sun is the fact that all of that mass is crushed into a volume, which is actually not very different than the volume of our solar system. So this is a fabulous XKCD comic that maybe some of you saw, marking out the sort of bounds of our human exploration, in physical form. So you can see there the Voyager mission. I'll point to it with my laser pointer right here. This is as far as the little Voyager satellite has made it. You can see Pluto's orbit here and our sun. This is obviously not our solar system inside the black hole. That would be a different kind of tragedy. But this is just sort of giving you a sense of scale. So this supermassive black hole has 6.5 billion times the mass of our sun packed into something that is the size of our solar system. And that's what makes it a supermassive black hole. That's what makes it a black hole. A large amount of mass crushed down into a very, very small volume. That volume and that mass are so extreme, the volume extremely small, the mass extremely large, that it traps photons. The black hole traps photons. So those photons that are coming, that would come from inside the very innermost regions of the black hole are in fact trapped in there. And so when I say we're observing black holes, the observations we make using electromagnetic radiation are always coming from just outside that event horizon. So they're coming, these beautiful photon rings that you're seeing outside the supermassive black hole are all of the hot gas and dust swirling and the photons swirling just outside the event horizon. All right, so let's just try to work a little bit more to get this picture of how compact these objects are. So let's put that in a little bit of context. So it turns out that our Earth, there's our Earth is 3.003 millionths times the mass of the sun. So, check out these numbers, right? You've got a supermassive black hole that's 6.5 billion times the mass of our sun. Then you've got this Earth that we love and sometimes care for, better or worse, that's roughly 3 millionths of the mass of the sun. And so this is a very small object, but we could still make it into a black hole, it turns out. So if we were to take the Earth and we were to crush it down to an extremely, so the mass of the Earth, and crush it down into an extraordinarily small volume, even the Earth could be a black hole. And so that includes like your mom and your dad and your grandma and the trees in the forest and everything that you ever thought of, our oceans, everything, our mantle, our core, gets crushed down into a very small volume. It turns out the volume it would have to be packed into to make the Earth into a black hole is something like the size of a sugar cube. Or you could imagine, if you prefer to play games, something like a standard rolling die. So that's what it would take to make something as compact as the mass inside this beautiful supermassive black hole in the galaxy M87. So here's a video that just helps zoom us in. So in case you've never located this supermassive black hole in the sky, it is in the direction of the constellation Virgo. So our movie is zooming in toward the constellation Virgo, and it turns out that M87, the galaxy that this black hole lives in, is inside of a huge cluster of galaxies known as the Virgo cluster. M87 is the brightest cluster galaxy. It's the brightest in this collection of galaxies, and already you can see that M87 is unusual compared to the things around it. It's got this spectacular bright jet, and we're zooming in and zooming in and zooming in and zooming in, and way down in the heart of this really massive galaxy, we find this supermassive black hole. So the thing that's amazing about the video I just showed you is that almost all of that is data. Those are real observations we have made with an entire array of different observatories across the entire electromagnetic spectrum that have allowed us to look not only in the direction of the constellations, these asterisms, these stars that we see superposed on the sky and that compel so many of us when we go out camping and look at the night sky, but we've probed further and seen other stars that are on the outer edges of our Milky Way galaxy, and then outside of our Milky Way galaxy to the next galaxies, and then not just to the next galaxies, but to whole clusters of galaxies that reside far from us. And then buried down in that cluster of galaxies, this really spectacular example of a very bright galaxy with a huge jet and a very massive, supermassive black hole. Again, just to give that a little bit of context, we think we live in a spectacular galaxy, and in many ways we do. The Milky Way galaxy also hosts a supermassive black hole. That supermassive black hole is called Sagittarius A star because, once again, if you were to look toward the direction of the constellation Sagittarius, you would be looking toward the center of our Milky Way galaxy. And that supermassive black hole is also impressive. It has millions of times the mass of our sun, roughly 4.5 million times the mass of our sun. So that's not a billion. So it's a few hundred, it's about 100 times less massive than this amazing black hole we're looking at the image of right now, but it's so much closer. It's also about 100 times closer. So we really hope the Event Horizon Telescope collaboration, which I'll talk more about in a minute, me, many of my colleagues, many of the folks working in my research group, we all hope to be able to present to you sometime soon an amazing image of our own black hole, one that is similar to this beautiful one you're seeing of M87. All right, so what's going on in this image? Here's another, oh, we don't want that video, we want this video. May it play for us? Yes, okay, so this is now an artist's impression. So we're not looking at real data here. We're looking at a kind of combined simulation environment of that hot gas. And then we switched away from looking at the gas, and now we're really looking at a simulation of the photons orbiting around the black hole. So why do we see this ring? Why do we see this sort of like donut of light on the sky? So it turns out all these photons are in orbit around the black hole, as is the gas and the dust, and they get trapped by the black hole because they are interacting with the gravitational field, the strong gravity around the black hole. They get focused by the black hole and sort of twisted and bent into this ring that we see juxtaposed on the sky. So this is the simulation image of what a sort of idealized, sort of example of a black hole might look like inside of a simulation, where you saw all those beautiful photons tracing out their paths as they orbit, and some escape and many get trapped in the vicinity of the black hole. And so now just juxtaposing that with this amazing image that we've taken using telescopes, and it's real data observing these photons and gas and dust around the black hole, you'll see the same ring, the same amazing gravitationally lensed ring that describes all the material and the photons around the black hole. But you'll notice it doesn't look perfectly uniform in all directions. So you'll see a brighter structure along the bottom of the black hole. This is actually really interesting. It has to do with a little bit of boosting that light gets, because the material and the photons on the bottom side of the black hole in this image are moving toward us, and the stuff on the top is actually moving away from us. And that little extra bit of boost that you get because you're moving toward the line of sight of the observer actually enhances the emission at the bottom of the image. So this is also telling us a lot about the theory of general relativity in the vicinity of a very massive object. We sometimes call that strong gravity. And we can use this to really test and probe GR, general relativity, and come up with all sorts of other interesting probes about what happens to particles and photons in this very extreme gravitational environment. It's extreme in a lot of other ways too. Oh, sorry, this is just a little shout out. So this amazing discovery, this beautiful image, was given the Breakthrough Prize and was also designated as the Breakthrough of the Year in 2019. So before I go talk about more physics, let me just take a step back and talk a little bit about people again. So this amazing discovery was acknowledged all over the world. People got really excited about it. And it was all made possible by this truly international suite of observatories. So here you're seeing observatories. You can see that they're pinpointed at locations all over the world. It requires a network of telescopes that span the entire globe to get a kind of a quasi dish that has the diameter of our whole Earth in order to make these beautiful images way down at these teeny, teeny, teeny little angular size scales. So without the entire international network, this experiment would not be possible. And we're working to add more observatories to fill in more gaps and make this a more complete suite of observatories spanning the whole globe. The observatory also uses the rotation of the Earth to get different, we call them baselines, different combinations of observatories looking at the telescope at different times. And so this is really an incredible effort. It has been just colossal work to get all these different observatories working together, integrated into the same analysis scheme, the same data acquisition schemes, and then just to get out there and hope for beautiful, perfect weather at every location we want to observe all around the world. So it's a tricky experiment. It's really a lot of work and really an impressive endeavor. And the telescopes are amazing, but these people are also amazing. So this is a snapshot of a subset of the Event Horizon Telescope collaboration, which involves more than 200 scientists, 60 institutes, including our own here, the McGill Space Institute, 80 countries, 6 different continents. So it's really just an incredible collaboration, really an amazing and diverse group of people that could always use more wonderful, brilliant young people involved. So if you have a passion for astrophysics, you know, some of these collaborations, they're kind of huge and a little bit overwhelming, but really, really dynamic and exciting too. All right, so back to M87. So I told you that there's this amazing strong gravity and we're probing these photons and it's an incredible feat. But the other thing that's amazing is that we can probe not only that smallest scale, but we can then march out and probe larger and larger scales using different telescope setups and different wavelengths of light. So at the bottom, this image I'm showing you here is a composite. These are all long wavelengths, so radio and sub-millimeter images. Down here is this beautiful Poehi, our lovely M87 supermassive black hole. And you can see here a it's about 0.003 light years across, a very small object. That small object is buried down inside of a larger structure that is visible at radio wavelengths. And you can see here, you might have noticed this in the video too, you can see here that this structure seems like it's kind of got 2 different sides. So it turns out this is actually our image of the jet coming from this supermassive black hole. It's sort of angled toward us. And what you're seeing are sort of the 2 sides of that jet, where we see a little bit of extra emission, where the sort of long edges of the jet are aligned along our line of sight. And so you're already resolving the jet. When you march out even a little bit further, you can see that jet is really, really bright and very impressive. And then check it out at really large scales. Now you're looking way out beyond the edge of the galaxy. And you can see that this jet just spews incredible energy out to enormously large size scales, now looking at 3,000 light years. So this itty bitty thing that's 0.003 light years across over many orders of magnitude is impacting the energetics of its galaxy and of its whole environment. So this is the radio wavelength. This is probing some interesting magnetic structures. Typically, radio emission often comes from the spiraling of electrons along magnetic field lines. But my team often works at a different energetic wavelength in the X-ray. So here, once again, is a very zoomed out image of this beautiful galaxy, this brightest cluster galaxy, M87. You can see amazing different structures, tendrils of hot X-ray emission, and buried down inside, we once again can see this very spectacular jet-like structure. Here's a zoom in of it. You can see it's brightest down very close to the supermassive black hole, but then there are knots also. So when you look in the X-ray, you're actually probing material that's extraordinarily hot. So the temperatures here are 1,000,000, sometimes even more degrees Kelvin. So really, really hot environments. And you can see once again that this jet is extraordinarily energetic and all being driven by this tiny, tiny, tiny little object way down in the center. And these other tendrils are probably interactions of this galaxy with all of the hot intergalactic medium all around the galaxy in this incredible galaxy cluster. So the Event Horizon Telescope collaboration is really, really excited about generating these incredible images of supermassive black holes, but it's also very excited about trying to connect those supermassive black holes and the gravity, the strong gravity regime that they're operating in up to larger and larger scales so that we can start to understand this sort of profound interaction that we've been exploring for many years. It's called black hole galaxy interactions. So, and we use the term feedback for trying to understand how the two different systems, the one on very large scales and the one on very small scales, interact with one another and guide each other's evolution. All right, so here's a little bit of I have two sort of little pictograms trying to explain a little bit about what we're seeing when we look at this, at these beautiful, very, very small black hole images, and then also the ones at larger scales. So here in the center is this EHT image of the black hole shadow, of M87's black hole shadow. And then if you zoom out, you're looking out toward this larger accretion structure, material flowing around the supermassive black hole, which drives this amazing jet that you've now seen, real observational evidence of this incredible jet. And trying to connect up what changes in the black hole might cause as changes in the jet or vice versa is a real feat, is something that we're using every simulation tool we can think of and every observation that we can think of to try to connect these together. And of course, we can not only zoom out, we can also zoom way in. This is a simulation now, a computer simulation of what we think the photons might be doing in the vicinity of the black hole. You can see there's a whole lot of structure here, which is blurred out. We don't see this kind of very fine structure when we look at the black hole itself. It's blurred out because we don't have perfect observations. But our simulations can trace every single little photon through this incredible strong gravity regime, and we can trace them as they orbit around. And different degrees of brightness have to do with that material moving forward or moving toward you or away from you as the observer, but also how many times the photon goes around the black hole. And these create many, many, many ring structures that are all superposed together and then blurred out by our inability to make a perfect image. So we're working very hard on these simulations, improving them, helping them do a better job of informing how we understand the observations that we make, and vice versa. So this is really exciting. It involves all sorts of amazing different techniques, including machine learning and deep learning and Sgr MHD, so general relativistic magnetohydrodynamic simulations, which require that we have a very good handle on not only all of our computational techniques, but also on particle physics and understanding general relativity extremely well, and understanding radiation and astrophysical phenomena very well in addition. So I have the second graphic. I won't go through all of the details again, but I wanted to have this one in here because I really like this depiction over here of this accretion disk to just help you remember that that large scale jet structure we think is really indicative of a strong magnetically controlled structure. So here is that accretion disk on the inside, but then somehow this little tiny black hole is driving this extremely collimated, very tightly bound magnetic structure that we call a jet. And electrons rotate along these magnetic field lines and create the radio emission that we see. And we think this jet is, again, as I've mentioned before, kind of headed somewhat, not perfectly along our line of sight, but somewhat in the direction of the Earth, which makes it more prominent and easier for us to observe it in some ways, harder in others. Okay, so I will just sort of say that it's really fun for me to come around and to be studying, the dynamics of these photons as they orbit around black holes, and to think about all these very, very complex and interesting phenomena. Because as students who are taking my introductory astrophysics course know, I got really excited about astrophysics when I was in university, because my professor helped me understand that we actually can use the gravitational fields of planets in our solar system to slingshot spacecraft out to larger and larger distances in the solar system. These are called gravitational assists. And so now I'm studying black holes who are giving some of those photons some really strong gravitational assists. This is a beautiful image borrowed from a poster that shows all of the solar system missions that we've launched from our Earth and all of the orbits that they undergo as they travel further and further out to explore our solar system. All right, so I said I would talk about observing black holes large and small. I have given a little bit of short shrift to the small ones, but let me just tell you another really exciting thing that my research group spends time thinking about, and that is the mergers of much smaller black holes. So these now are black holes that might have masses more like 10 or 20 or maybe as many as sort of 60 or 80 solar masses. And these are binary systems. So here you have two black holes that are orbiting around one another, or maybe a black hole and a neutron star that are in orbit, or perhaps not black holes at all, but two neutron stars orbiting around one another. And as these objects orbit, they perturb space-time, and they emit this different emission. It's not electromagnetic emission. It's called gravitational waves, or gravitational wave emission. They are literally ripples in space-time. And we detect those here on Earth as those gravitational waves actually take our Earth and kind of slightly squish it a little bit, which is phenomenal. And so this is done using the amazing LIGO Laser Interferometric Gravitational Wave Observatory. That's LIGO, and its companion Virgo in Italy. There's also another detector called Sgr A coming online just recently in Japan. And then we hope that there'll be another part of that array that takes place that gets set up in India as well. And so once again, just to emphasize the very collaborative and international nature of these really enormous astrophysics experiments. So in this case now, we're studying these objects, but they're originally detected not via their light, but via their gravitational radiation. And so you're seeing that here. Here are two stars, two black holes orbiting around one another and emitting these ripples in space-time. And so this is also very exciting. And when we take these gravitational signals and we combine them with some other cosmic messenger, that might be photons, that might be neutrinos, that might be cosmic rays. So those are our four cosmic messengers: neutrinos, cosmic rays, gravitational waves, and photons, or electromagnetic waves. When you combine any two of those together, you're doing something that we like to call multi-messenger astrophysics. So Adrian said I was the Canada Research Chair for multi-messenger astrophysics, and I am proudly that person. So this is a very cool and exciting new arena in which we can study the smaller black holes. So these are not supermassive. They're not millions to billions of times the mass of our sun. They're hundreds of times or tens of times the mass of our sun, but they're in these really interesting binary systems. So I'm going to first start, I'm taking a little bit of a left turn. We're going to talk here first about actually two neutron stars, so not black holes at all, merging together. But this was the first truly multi-messenger, gravitational wave multi-messenger event that we saw. So this is two neutron stars smashing together in a beautiful galaxy. This is a lovely fade from the Hubble Space Telescope image showing you what this galaxy looks like in the optical and infrared, and then it fades to the X-ray, so the higher energy emission. And so this is the host galaxy of the event, and this white box is here conveniently showing you this explosion that occurred, the light from this explosion that occurred when these two neutron stars orbited around one another and lost so much energy to emitting those gravitational waves that they actually collided and smashed together, which created a big explosion called a kilonova. So this was really exciting. This took place, it was detected in 2017, and once again was also given lots of excitement. It generated a huge amount of excitement, this first multi-messenger event. But actually, LIGO and Virgo spend most of their time looking at black hole mergers, not at neutron stars merging with each other. And so this is a really lovely updated plot that they refer to as the masses in the stellar graveyard. So we think these smaller black holes are mostly born in stellar explosions. So you have a massive star that burns through its hydrogen very quickly. And when it explodes, it leaves behind a black hole or a neutron star. And so that's why it's masses in the stellar graveyard. These are the remnants of exploded stars. And you can see here highlighted, this one's updated by by multiple colleagues at Northwestern, but a close friend, Aaron Geller. So this event up here at the top is highlighted. This is one of the most recent and exciting discoveries. As you can see, these black holes sit way at the top. Oh, I should have said here that the plot we're looking at here is showing you the mass of the object in solar masses. So much the way I used the sun to be my marker for stellar, for black hole mass with supermassive black holes, I'm doing the same here with the low mass ones. So this object here probably has a mass of like 50, 48 solar masses, something like that. So these, this merger here, so these are the two black holes that merge together to make this one. This is a really exciting event. It was just announced earlier this month. It's a very exciting event because these black holes are by themselves extraordinarily massive, and this remnant is very massive. So you can see it sitting up there at 160, 150 something solar masses. That's a really massive black hole. And it's kind of mysterious how you make these huge, massive stars that collided together. And it's even more cool to observe one up here at the very high end of the mass spectrum. So that's very exciting. And this is some like latest and greatest black hole merger news coming out of the LIGO collaboration. But my team has not worked on this object. So it turns out when you smash two black holes together, it's really hard to detect them, especially if there's none of that hot material around it. It's sort of like something big went bump in the night, and you detect it in gravitational waves, but you don't detect it electromagnetically. So all of these black hole mergers that you're seeing up here at the top of the plot, we don't see any electromagnetic radiation from them because they're black holes. They don't emit light unless they happen to have hot material around them. And so when two of them merge together, they only emit gravitational radiation. They don't emit electromagnetic emission as far as we can tell. So we haven't had any multi-messenger observations of these top ones, but down here you get a little bit more spicy about maybe getting a multi-messenger observation or multi-messenger detection. And so the very first one of these is this one here. So this is the event GW170817, which I showed you that pretty fade image of. So this is two neutron stars merging together. This is the first time we detected a double neutron star merger, and it's the very first time we saw gravitational radiation and electromagnetic radiation from the same source. So this was a huge deal. It was very exciting. And me and my team here at McGill, including multiple fantastic postdocs and grad students, worked really hard on this. Most recently, one of our moderators here tonight, Nick Vieira, actually went after another really exciting source. So this is potentially the first black hole plus neutron star merger, right? So we talked about two black holes merging. We talked about two neutron stars colliding and smashing together and exploding. But what happens when you smash a neutron star into a black hole? So we have some ideas. We think it might also lead to an interesting explosion as the neutron star gets sort of shredded apart by the black hole. So this is the first time that LIGO Virgo have detected an event that could be one of these. You'll notice the question mark down here. You might have noticed there was a question mark here too. We don't actually know when you put those two neutron stars together, when you smash them, we don't know if you got out a neutron star or a black hole. Probably a black hole. And in this case, there's also a question mark. That's because we don't know whether this second object was just a very, very low mass black hole or a very high mass neutron star. So, and then so this object, this mystery object, merged together with the black hole and made a slightly more massive black hole. So you can see that the zone in here, which we sometimes refer to as a mass gap, if I get my pictures out of the way, you can see here, this is the mass gap. This is a really interesting domain to probe using this sort of multi-messenger technique, because you can see all the little question marks live in here. We don't have very good models for understanding what's going on in that in-between zone between the neutron stars and the black holes. So that's very ripe and exciting and interesting for discovery and future learning. Okay, So I'll just give a shout out here again to Nick, who worked really hard. So as I mentioned, this object was detected with electromagnetic light and with gravitational waves. And I mentioned this one might have a neutron star in it, and maybe that could create some sort of very explosive emission too. So the whole world went after trying to observe this object as well, this merger, to see if we could see light from it, including our team here used the Canada-France-Hawaii telescope. You can see this is our very hard-won effort to try to trace out and probe all the whole region in the sky where we think this event might have occurred. And the sad truth is that none of my team and nobody in the world ever managed to detect an electromagnetic counterpart from this event. That might be because the question mark source was a black hole, and it was just two black holes merging, so there was no emission. Or maybe it was just because it was too faint and too far away, and we just weren't quite able to get at the emission. It was just a little bit too faint for us to tackle it. So that's it. Thank you all for being here. I know we have a lot of questions. I'm more than happy to take questions. I want to make sure that I take a second to bring us back to where Adrian started today. So this is a little image of a t-shirt that I gave all of my group members. And we've been talking about whether or not we can't acknowledge some of the both hardship and also beauty of our communities. And I just want to remind you that not only are black holes amazing, but that Black lives matter and that Indigenous lives matter, and that we've got to keep all these social issues way up the top of our minds and hearts, and participate as much as we can while we're also tackling all this science that we're excited about. So with that, I'll take questions.
Thank you very much, Daryl. And as you correctly guessed, we already have a lot of questions. So I will pose some of them to you and to the audience. If we don't get to your question, don't worry, I'll be putting up our outreach email address at the end of the night, and you can always feel free to send us more questions if you have them. And also in some cases where we've gotten similar questions, I'm going to paraphrase some of them, lump them together just for efficiency. So Daryl, one of the first questions we have is you talked about the this jet coming out of this supermassive black hole, and you also talked about these particles, these electrons that are resulting in these jets being super bright and giving off emission. But what's the jet made of? Is there stuff in the jet? Is it a hollow tube? What is it?
Yeah, that's such a good question. We would all really love to know the answer to that question. So that's a deep question. We do think it's sort of a hollow tube. I mean, if our models are right. So it's difficult for us to go. So I hope that I impressed upon you that our actual ability to go out and explore space, with physical detectors and spacecraft is very limited. We've only made it out to the very edge of our solar system, and our star doesn't have a jet. So we don't get to send a probe to study jets. So we instead model them, we observe things, and we try to build models that do a good job of explaining all the observations. So with that important caveat, we've never gone to a jet and really looked at it, but we think the model we hold for them, sorry, I don't know if you can see my hands very well, is that they originate down near the black hole, maybe embedded in the disk, that accretion disk, and they are kind of like a hollow tube. And that's partly got to do with the fact that we think that they are coupled to the accretion disk. So imagine something kind of flat like a frisbee, where there's a lot of material sort of confined to that plane rotating around the black hole. And now imagine that you've got a magnetic field that goes like this through that accretion disk. And now take that magnetic field and kind of pin it to your frisbee and spin your frisbee. So all those magnetic field lines that are in the disk get twisted. So that's sort of the way we think of jets, as being this sort of twisted magnetic field structure that is originating in the disk and getting kind of wound up, maybe by the rotation of the disk or the rotation of the black hole. And so there's material and plasma and emission along the edges, along the kind of outside of that funnel. And maybe there's plasma on the inside. It's a little harder for us to look right down the centers of the jets. So in answer to your question, there's lots and lots of interesting particles, lots of electrons, lots of photons, and the environments are so hot that they're usually in those sort of those constituent particles, and lots of hot plasma. But there was also maybe, plenty of empty space. Everything in space is pretty sparse, it turns out. So even though they look really magnificently bright and energetic to us, there's, it's probably wouldn't feel, if you were near it, feel like a sort of a whirling tornado or anything. It would be very energetic, but maybe not very mass loaded, we say.
Okay, thank you. So marching right on, here's a question about supermassive black holes. And this audience member says, yep, understand that like there are often supermassive black holes at the centers of galaxies. Are they always there? Do you find ones that are not at the centers of galaxies?
Yeah, also a profound question. So for the supermassive black holes, it's difficult for us to detect them. This is true actually of all black holes. It's difficult for us to detect a black hole if it's not interacting with something else. So the black hole that is interacting with the hot gas and material around it in accretion disks and jets, that we detect electromagnetically because it's heating up all this material in its vicinity, energetically as they interact. Or the gravitational wave sources where you've got two black holes or a black hole and a neutron start interacting with one another. Those are the conditions in which we can detect black holes. Isolated black holes just lurking around in between galaxies or hanging out in our solar system, or really, well, solar system we might notice because it would dynamically shake up our solar system, but we don't see them very easily. So I sort of gave away one possible thing. You could see it dynamically interacting, and people actually did a study like this called super macho, where they wanted to know whether or not this other really fascinating phenomena called dark matter could be attributed to black holes. And they went out and they just stared at a patch of sky. And what they were looking for is this really neat phenomena called gravitational lensing, which I mentioned a little bit. So where the black hole actually kind of bends light into your line of sight and makes something look brighter for a second. So if you have a star at my position and you have some little black hole go by in front of it for a minute while that star and the black hole are aligned, the black hole sort of focuses light in your direction. So people went out and looked to try to see if we have lurking black holes, and they didn't find anywhere near the number you would need to explain dark matter. In fact, they found very few. So it looks like most black holes are in the hearts of some sort of dynamical system, maybe a cluster of stars, maybe a star formation region, maybe in the center of galaxies. In answer to your first part of your question, we think for massive galaxies that there is always a supermassive black hole in the middle. Our certainty in that response, our confidence decreases as you go towards smaller and smaller galaxies. So little tiny galaxies called dwarf galaxies, some of them may host black holes, some of them may not. We're not 100% sure whether they have black holes or whether they don't have supermassive black holes at their hearts. So we're still working on that. It's actually very important for understanding how supermassive black holes form to kind of get at that low mass population. But it's much harder to observe those galaxies and those supermassive black holes or intermediate mass black holes.
Great. So this one actually kind of follows on directly from what you were saying, which is, I understand that black holes can be born after a death of a massive star, but you're talking about black holes that are billions of times the mass of the sun. What are some ideas for how these gigantic supermassive ones form?
Yeah, that's a great question. So we think that they grew. I'll come to how they form in a second, but we think that they grew mostly by accretion. So just huge amounts of mass getting kind of funneled along in the early universe, funneled along all sorts of streamers in toward the central parts of galaxies as galaxies were forming. So you have over densities of dark matter, baryons, so stuff that we think of as matter, collects into those gravitational groupings, and then it gets kind of funneled in more and more as it grows. And so you are basically funneling a lot of gas and dust in toward the central region, and that can allow a black hole, if there's a black hole in there, to grow very quickly. It's actually hard to get them to grow all the way to supermassive sizes or masses as fast as we need them to be able to have the things that we observe in the early universe. So it's actually hard to shove mass in there as fast and as kind of in large enough quantities to really make supermassive black holes. So that's that's like at least one idea. It's called accretion. It's basically just mass flowing into the black hole very, 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 very rapidly. So that's how we think they grow. How do they form? That's a great question. People are working really hard on trying to understand the formation of the earliest black holes. We sometimes call these black hole seeds. So indeed, you're correct. If you wanted to build a supermassive black hole, it would be really hard to take, a whole bunch of 10 solar mass black holes that grew out of explosions and smash them all together to make something that's 6.5 billion times the mass of the sun. That'd be a lot of supernovae. So instead, people think maybe very massive clouds directly collapse into black holes, or perhaps there are a series of mergers that build up enough of a remnant that then can grow very rapidly by accretion. But the jury is still out there. We're still working really hard to probe observationally back far enough in time, understand when the supermassive black holes are already supermassive, and then build our theories around those observations and try to kind of piece it together like a puzzle.
Okay. So speaking of puzzles, this is one of our paraphrase of one of our pre-submitted questions. So this audience member says that they recently read about some of the most actually you alluded to this, some of the recent gravitational wave results, these mid-sized black holes, and they've read about how this was supposedly surprising. Are they surprising in a way that means that we found ways that we need to rethink general relativity, or is it surprising in a different way? What does it mean?
Yeah, so not yet that we are rethinking general relativity. So both the Event Horizon Telescope and the LIGO experiment have worked really hard to see whether or not we can detect any deviations away from our predictions for general relativity in the observations we've made through these two different streams, through supermassive black holes and mergers of lower mass ones. So far, we haven't seen any really interesting deviations away from general relativity. Physicists love to break models. It's how we learn new things. So, it would be fantastic. We'd love to break GR, but we haven't done it yet, at least not in these experiments. And so that hasn't yet blown our minds. You'll hear about it, I think, if it does. The challenge that these black holes offer right now is that they're really massive. I mean, the two constituent masses are 85 solar masses and 66 solar masses. So think in your mind for a second, if you want to build a black hole that's 85 solar masses, that means you had to start with a star that had hundreds of solar masses. Maybe it loses 30% of its mass in the explosion. But even before that, for really massive stars, it turns out that they drive very strong winds and they lose a lot of mass even before they explode. So then you have to start with an even more massive star. So maybe you had to have a star that was 200 solar masses or even more. And when we look out in our galaxy and in neighboring galaxies, we don't see stars that have 200 solar masses, at least not very many. In fact, maybe none that are that massive. I'd have to go back and figure out what the record holders are now. But those massive stars are not there in very large numbers. So then you don't quite know, like, how did you build such a black hole? How did that proceed? What was its evolution like? And we don't have very many examples to train our knowledge about how you create the black hole and what sort of stellar evolution led to that remnant. So it's very interesting. Maybe these are mergers. Maybe there were two black holes that merged together to make the 85 solar mass one and two black holes that merged together to make the 66 solar mass one. And then those, merger remnants merged together. So there's a lot of different thinking going on for how we could try to marry this new observation with the things that we've built up as theories over the last many decades.
All right. Thank you. And now a few questions about the black hole picture that you showed earlier. So you said that the particular shape that we see is because of the direction in which things are going. So one of our audience members asks, if the photons on top are moving away from us, how can we see them?
Yeah, that's a good question. So they're a flow. So the ones that we see definitely were coming toward us. Thank you. That's a good clarification. But there's a sort of an extra an extra boost. So you have to think of the whole thing as sort of spiraling around. And then the ones that are moving toward us get this thing, it's like a Doppler shift. So some of you maybe have heard about Doppler shifting. So for example, imagine when the ambulance goes by you, it goes wee, 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 wee. That's a Doppler shift. So when something is moving towards you, the frequency looks higher and then it looks lower. And so we actually get that when the photons, when the stream, the accretion flow is moving toward us, everything gets kind of pushed together a little bit more, and it moves to higher frequencies and we see it more brightly. And then when it's moving away from us, it's a little bit depressed in the other direction. So there's that, and there's other kind of beaming effects that happen because of the strong gravity. So yes, indeed, you are correct. We are always seeing the photons that were headed in our direction. It's just that the bulk of the flow has this kind of overall dynamic that guides the way the photons get received on our end.
Okay. And just a very related follow-up here. Are all of the photons kind of trapped like this, with some of them kind of beamed towards us, or do some of them, fall into the black hole? Do some of them get scattered into other directions in space? How does that work?
Yeah, so the answer is yes, 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 and yes. So all of those things happen. Some of the photons get trapped inside the black hole. Some of them end up in making the very final ring. They can actually make a beautiful photon ring, a perfect circle. It's the last stable orbit for a photon. So think about that. That's amazing. So there is a final stable orbit for photons in the vicinity of the black hole. And those can be stable orbits. That photon could just live there forever, stably orbiting around the black hole, the same way our Earth stably orbits around our sun. But some of the photons do, head off in all sorts of different directions, and some of them spiral for a while and then get kicked out, and some of them spiral for a while and get kicked in. And so some of them do end up getting trapped, and some of them actually end up coming here so we can detect them.
Okay. Now, another question, and this one kind of about the similarities and differences between, say, M87 and our Milky Way's black hole. So you've showed these graphics where you've got these black holes with all sorts of crazy activity going on. Can that happen for the supermassive black hole in our Milky Way? Like, has it happened? Could it happen now? Is it happening now?
Yeah, so the answer to is it happening now is definitely not. So we are a really quiet, we call it quiescent. We're like a super sleepy galaxy right now. Our supermassive black hole is not growing very much. In fact, material that tries to get into our supermassive black hole often just gets pushed right back out. So our black hole is not really doing much of anything. It has a tiny little trickle of material around it. We actually think that the amount of material accreting onto our supermassive black hole is entirely coming from stars that are in orbit around the black hole. And you remember I said massive stars launch winds. So the massive stars actually they loft some material off the surface of the star. We think all of the material accreting onto our black hole, Sagittarius A star, is actually coming from these stellar winds. So it's just little puffs of mass coming from all the massive stars that are orbiting around the black hole. So there's not that much mass in there, and there's no bright jet. We have searched and searched and searched to try to find a jet in the vicinity of Sagittarius A star connected to our supermassive black hole, and we cannot find it. We think it's there. It's possible it's really hard to see because it's pointed straight at us, and that just like makes it really difficult to make out the jet structure. Maybe that's one scenario. So we think there should be a jet, but we don't see one. And even if there was a jet, it's a very, very faint system. It is nowhere like the M87, amazing, enormous structure on those huge size scales. So M87 and galaxies like it, we call sometimes active galactic nuclei. The most extreme examples are called quasars. So they're rapidly growing. They have very bright accretion disks. They often drive these very bright jets. And our Milky Way galaxy's black hole is not growing like that. There's not enough mass flowing into the Milky Way right now. Your other question about whether it ever has been like that is, yeah, we kind of think it might have been in the past. Maybe not quite as spectacular as M87, but we see some evidence. They're called Fermi bubbles, these beautiful, big, huge gamma ray bursts, gamma ray bubbles that are above and below the plane of the Milky Way galaxy. You can go look those up. They're really, really cool. And they kind of look like some energetic process in the center of our galaxy actually ejected a bunch of stuff and heated up all this really amazing gas to very high temperatures, and they're huge structures above and below the Milky Way galaxy. So that could be because of our supermassive black hole. It could have also just been a burst of star formation that caused a whole bunch of supernovae to go off in the middle of the galaxy around the same time. So there's always different scenarios we wrestle with, but that probably, if it was growth of our own supermassive black hole, an event connected to that, I think that the expectation is that that happened, I might get this wrong, but I think it's around 10,000 years ago. We have some other evidence that there might have been another burst of activity more recently, about 400 years ago. But still, even then, it's very, very trace evidence, and it probably wasn't very bright or sort of incredible the way that the M87 jet and emission looks.
All right. So we're 4 minutes until 8 o'clock, so I'm going to do 2 more questions. One is another one of our pre-submitted questions, which is there anything that an amateur with a moderately sized telescope can see in the night sky related to black holes, or do you really need extra equipment and then professional grade telescopes to do anything?
So that is a good question. I don't know the amateur technology very well. So there's a huge range, right, between a sort of a simple thing that you might be able to borrow from your university or get your hands on, through McGill or your local library or wherever you might be able to access that. And then there are people who have amateur telescopes that are actually like very fancy and can do a lot of things. So there's a big range there. I think probably the best you can do with a sort of medium-sized, pretty nice, but still amateur telescope is you can go and you can actually pretty easily observe a lot of the objects in the Messier catalog. So I told you that M87 has a historical name. M87 is a Messier object. And so Messier went out, this was a guy who lived a long time ago, didn't have fancy telescopes like we have now, and created this beautiful catalog of objects that looked interesting in the sky, often because they were kind of fuzzy. And he was looking for comets because the king really wanted comets because they thought that it was going to tell them, what their fate might be as a leader and things. So anyway, Messier went out and dutifully looked for comets. And so he was looking for anything fuzzy and ended up creating this like really amazing catalog of objects that turn out to be everything under the sun. Some of them are galaxies, some of them are planetary nebulae, some of them are supernova remnants. And one of them is M87, the galaxy that hosts this supermassive black hole. So for sure, if you had a pretty nice amateur telescope, or even a moderate sized telescope, you could see M87, the galaxy. And maybe the jet, but some parts of the jet you might be able to make out, but probably not, because that's mostly going to be, if you had a radio telescope, you might be able to see something. But in general, all of that tiny scales that we are showing you in these beautiful data are really only accessible with very, very, very intense equipment. And even then the techniques are still really challenging for us as professionals to go out and collect certainly those black hole images. I should say though, that there are lots of black holes living in our galaxy. So supermassive black holes, there's usually only kind of one per galaxy in the middle, but in the rest of the galaxy, there's tons of little ones roaming around. And those little ones often do have accretion disks. And so if you could put on your X-ray glasses, you could go out and maybe look at some of those, but that's tricky here on the Earth because the X-rays, thank you, atmosphere, are blocked by our atmosphere.
Okay, so one final question in the minute we have left, which is kind of relates to telescope technology as well. Could you say a few words about the future of VHT, whether there are technological improvements that will make these black hole pictures even better, or maybe there aren't? What's your view on that?
Yeah, so there's lots of excitement about thinking about those questions inside of the EHT collaboration and even in a slightly larger community. So one of the things that that has proven to be true is that, so when the EHT first started, one of the most important things they were looking for was the longest, I called them baselines. So the longest line across, at least one side of the globe. So they wanted long baselines to try to get the largest sort of quasi diameter for their world-sized telescope. But then it turns out that actually filling in all the smaller connector baselines, so less long, but many more of them, actually really helps you fill out the image and get a lot more data and a lot more, not quite resolution, but a lot more sensitivity. And then you can actually do more when you try to extract science out of the image. So that's one idea, and that's already been approved, actually. The NSF has improved the early development of a new network, an upgraded network called the Next Generation EHT. So you'll see that abbreviated sometimes as NGEHT. So that's already getting going. We're actually working on the development for that, thinking about what technologies we need and how do you make all those telescopes work together correctly, and how do you get the computing power to actually see all of the sky from all those different sites as if it's one telescope. It's very tricky. So that's one kind of near-term thing that is going to happen, is filling in a lot of those baselines. The other thing that we are thinking about is how now, so that's great, we want to fill in those baselines, but if we really want better resolutions, we really want to see all those pretty little photon rings like in data, not just in our simulations, we need a longer baseline. And that means we cannot be confined to the surface of the Earth. If we want a really long baseline, we need a spaceship, a spacecraft. And so there are discussions about whether or not you could put a spacecraft in, say, low Earth orbit, maybe a little bit like Hubble or something that's orbiting around the Earth, that could network together with all of the Earth-based telescopes and make a interferometer with a longer baseline, or whether there's even constellations of telescopes that you could put on other interesting orbits. It's actually very fun working with engineers. I sat in a workshop about a year ago talking with engineers who do all of these incredible orbits for constellations of spacecraft that then are orbiting each other and then orbiting the Earth, and the whole thing is totally wild and cool. So going to space might allow you to extend that baseline and actually get a more high resolution image, but going to space is super expensive. And so there's always a trade-off. Also, it's hard to repair things in space, so redundancy becomes important, etc. So there's lots of ideas, lots of brainstorming. Zeppelins, could we tether Zeppelins up above the surface of the Earth, and would that give us a longer baseline? You know, people love thinking about this stuff. It's really fun. And so for sure, stay tuned. If you're interested in engineering or astrophysics or whatever, there's a lot of great kind of food for thought in thinking about next generation instruments.
Okay, well, thank you very much, Daryl, for an amazing talk and for answering all these questions. So to audience members who didn't have their questions answered, sorry about that. Our time is always limited. But if you want to send any unanswered questions to outreach@physics.mcgill.ca, we can do something about that. You can also send us an email to get added onto our mailing list, or follow us on Twitter or on Facebook. And we've got a very exciting lineup of speakers for you this term, including people talking about the Vera Rubin Observatory you might have heard about, talking about extrasolar planets and ultra-fast lasers, and all sorts of good stuff. So stay tuned, and hope to see you next time. Thank you very much.
Have a great night.